Thank you, everybody. My name's Peter Ashworth. I'm Chair in Sustainable Energy Futures at the University of Queensland, and it's my very great pleasure to introduce you to Professor Peter Hoy, who will do the welcome. Thank you.
Good morning, everyone, and thank you for coming. It's a bit hard to navigate between the tables, but that's a good thing. It's because we have so many people very interested in coming today. So first of all, I would like to acknowledge the traditional owners of the land upon which we gather and meet and pay our respects to elders past and present. It's a great pleasure for me as Vice-Chancellor of UQ to be here with you this morning. It's particularly a great pleasure for me to welcome Dr. Alan Finkel, AO, Australia's Chief Scientist, the Honourable Dr. Anthony Linham, Minister for Natural Resources, Mines and Energy, today's panellists, Mr. Gustavo Gomberg and Professor Peter Ashworth, sponsors, partners, all of you. It's wonderful to have you here. We do have a sellout crowd this morning, and it's a strong indication, I think, of the level of interest in today's topic and, of course, the caliber of today's speaker. These events that you're attending today have been running since 2011, bringing internationally acclaimed speakers from around the world to Brisbane to lead broad industry discussion of global energy and climate policy issues. Our intention is to promote a mature, well-informed and grounded conversation about the transition we believe we need to make to create a low-emissions future. While the series is not intended to be a vehicle for advancing policy advocacy on specific immediate policy issues in play, we do aspire, more broadly, to close the gap between science and politics. As the recent landmark report of the UN Intergovernmental Panel on Climate Change, the IPCC, reminds us, urgent and unprecedented changes are needed if global warming is to be kept to a maximum of 1.5 degrees C from pre-industrial levels. We at the University of Queensland envision that a mix of conventional and non-conventional technologies will be required to meet the world's growing energy demands. We try to lead by example in our research, our teaching, and our use of renewables to the extent that we are actually set to become the first major university in the world to offset 100% of our electricity through the use of our own renewable energy asset. We intend to become energy neutral by 2020 with the establishment of a 64 megawatt solar farm at Warwick to offset our annual electricity needs. We intend to generate 140 gigawatt hours in association with our existing 6 megawatt generating capacity. Today's discussion focuses on a relatively old concept, taking hydrogen to produce, store and use energy in a clean fashion and re-examining that in a 21st century context. Hydrogen, as we know, is the simplest and most abundant element in the universe. It's been known to science since the 18th century when it was described by English scientist Henry Cavendish. In Australia, creating a hydrogen economy has been frequently and consistently proposed since 1972 at least, without ever proving its competitiveness at scale. The appeal of hydrogen as an energy carrier is easy to fathom. Like natural gas, hydrogen can be used to heat buildings and power vehicles, and when burned, the only byproducts are heat and water. Indeed, that was the very reason why I, in the early 1980s, did my PhD on photosynthesis, which is probably the oldest example of a hydrogen economy. If produced using renewable energy sources, it can enable deep decarbonization across the energy and industrial sectors. Of course, it can also be produced from coal and natural gas reserves, with the impact, though, of a byproduct of CO2, which possibly can be mitigated by capturing and sequestering the carbon in underground storage sites at the required scale. Now, more than 40 years after a hydrogen economy was first proposed, meeting energy needs with clean hydrogen is finally becoming a reality, we believe. With the emergence of countries determined to decarbonize their economies using hydrogen, notably Japan and South Korea, unprecedented opportunities for Australia to produce hydrogen for an export market seems to be emerging. Australia's hydrogen potential has recently been explored in a briefing paper for the COAC Energy Council entitled Hydrogen for Australia's Future. It was prepared by the Hydrogen Strategy Group, a panel of experts who see the opportunities for hydrogen in our future economy, and it was of course chaired by none other than today's keynote speaker, Australia's 8th Chief Scientist, Dr. Alan Finkel, AO. Alan has an extensive science background as an entrepreneur, an engineer, an educator, a researcher, a philanthropist, and of course, a thought leader. Before becoming Chief Scientist, Alan Finkel was Chancellor of Monash University and also President of the Australian Academy of Technology and Engineering, ATSE. Dr. Finkel has led a number of national reviews, including chairing the review into the national electricity market, known as the Finkel Review. He's widely considered as one of the great science communicators of our age. That's why I'm glad there's a breakfast between Alan and I. It promises to be a fascinating insight into the benefits of an Australian hydrogen production industry. So I welcome you. I hope you will have a bit of breakfast and then you're ready to listen to one of the great communicators, but more importantly, one of the great experts in the topic that we're concerned with. So thank you all for coming.
But it's my very great pleasure to introduce our Chief Scientist, Dr. Alan Finkel, to come and share his insights about the way forward for hydrogen. Thank you.
Peter, thank you. Thank you, Peter. I'd like to acknowledge Minister Leinen, Peter Hoy, the Vice-Chancellor, my fellow panellists, Gustavo Gomberg and Peter Ashworth, and I'd like to tell you a little bit about hydrogen. Is the sound quality good at the back? Great. So, I'm going to talk about hydrogen as a fuel. The one I've got at the top there, I've written it as methane, but you all know it as natural gas, right? Natural gas is made of methane, carbon with 4 hydrogens. And when you burn it with oxygen, you get 3 things. 3 things. You get the energy you want, you get water vapor, and you get carbon dioxide. And the carbon dioxide is the thing that we don't want. That's the byproduct that we would prefer not to have. So you've got to say to yourself, what if there was an alternative that did not have CO2? And of course, hydrogen is the alternative that we're going to talk about. Hydrogen, just like methane, can burn with oxygen, gives you the same energy that you do want, the same water vapor that you absolutely don't care about. But the beautiful thing is the last box is empty. There is no unintended carbon dioxide or anything nasty. There's nothing nasty, there's no particulates. If you do it properly, there's no nitrous oxides. It's an ideal fuel. The problem is, you can't just go and drill a hole in the ground and find it. So Peter, you mentioned it's the most abundant element in the universe, but it's not freely available on Earth. But we'll get to that. Where do you get it from? The opportunity that we're trying to address is a massive opportunity for export, as well as domestic opportunities. And I'll go through those in detail. But they're both very, very significant. The question, of course, comes up, why now? And Peter, you mentioned 1972. You could go back to 1873. Well, actually, you mentioned photosynthesis, and that's nature, and we'll give nature the benefit of, or the credit for being first. But in 1873, Jules Verne wrote a science fiction book in which there was this Socratic dialogue between 2 characters talking about hydrogen can be extracted and be used as a fuel in the future and transform the country. And then in 1923, a very serious scientist named J.B.S. Haldane wrote a bit of an exposition on how hydrogen could be used to fuel the economy. And then in 1972, John Bockris, who was an American who was living in South Australia for 9 years, while he was working at Flinders University, wrote an article in Science magazine where he introduced the phrase hydrogen economy. So 1972, 46 years ago, and nothing's happened. So, it's not as if hydrogen hasn't been used. I'm going to address the why now, but it's not as if hydrogen hasn't been used. Hydrogen is used in enormous quantities for industrial chemistry. It's used to make ammonia for fertilizers and for explosives. It's used to make methanol for the chemical industry, and it's used as the petrochemical refining, in the petrochemical refining process. But despite the suggestions to be used as a fuel, it's never been cost competitive. Something's changed. The first thing is Japan. Japan wants to decarbonise their society. The problem is they are totally dependent on imported fuel. 94% of all of Japan's energy needs, whether it's for heating houses or for driving trucks or for generating electricity, 94% is from imported fossil fuels, oil, coal and gas. Nuclear's on the nose, they don't have much land, etc., etc. If they want to decarbonise, they need an alternative to some of their imported fossil fuels. And they have identified clean hydrogen or carbon-free hydrogen as that alternative. Their need, as an importing country, is our export opportunity. The second of three things that's changed is the dramatic reduction in the cost of production. In 1972, when John Bockris came up with the phrase hydrogen economy, you couldn't buy a solar panel. They just weren't available. They were only in use on satellites. The first time you could buy a solar panel for terrestrial use to generate electricity was in 1977, and the price has come down by a factor of 500 since that time. Solar panels to make electricity that will be used to make hydrogen. And then in utilisation, we've seen a dramatic drop in the cost of fuel cells. Fuel cells are the devices in a car or a truck that convert the hydrogen into electricity to drive the truck. Just in the last 15 years, they've come down by a factor of 20 in price, a factor of 4 in volume, a factor of 3 in mass. Everything's moving in the right direction. So where do you get it from? I said it's not freely available. You can't just drill a hole in the ground to get it. There are two pathways for producing hydrogen that we need. The first is what we call renewable hydrogen. Renewable hydrogen where we start with water, add some clean electricity, it could be solar, it could be wind, put it through a device called an electrolyser, and what we get out are two things. Basically, you put electrodes into a glass of water, but do it in a swimming pool and do it every second instead of every day. Put the electrodes in. On one electrode, you get bubbles of hydrogen. On the other electrode, in the electrolyser, you get bubbles of oxygen. The hydrogen is what you want, and the oxygen, you just let it go. Oxygen is a good thing in the atmosphere. We can't complain about that. So now we've got the potential for abundant supply of hydrogen. Just to emphasise the price reductions that we're seeing, I'm not sure if at the back you can see the bottom axis, but it's only going from about 2013 to 2017. The vertical axis is in US dollars per megawatt hour, so that's the price of electricity. And across the world, we're seeing just in the most recent 5 years, 4 or 5 years, a dramatic decline to the point where in the last 2 or 3 that are on that graph are below $20 a megawatt hour. That's a stunningly low price. And my estimates and those of the CSIRO for long-term price targets are to get down to about $10 per megawatt hour in the 2030s. We'll do it easily. If you're a chartist and you believe in extrapolating, we'll do it easily. The other way to make hydrogen is from a fossil fuel pathway, but then you need carbon capture and storage. So for the fossil fuel pathway, you can do it from coal or methane. You start with a fossil fuel heat source, you add some water vapour, so we're reversing what you saw before, and the two things you get are the hydrogen that you want and the carbon dioxide that you don't want. Now, Japan won't buy our hydrogen if we just let that carbon dioxide go into the atmosphere. So that carbon dioxide has to be dealt with. We have to capture it and store it for the long term, and I'll come back to that in a minute. It doesn't have to be methane, it could be coal. Once you've got the hydrogen, you want to send it somewhere, or you want to use it domestically. Let's look at the export opportunity first. How do you ship it? Well, the obvious way to what I've called shipping sunshine, I'm working on the renewable pathway in my mind at this point. The obvious way to ship it is to do a physical transformation, just like we do with natural gas, from the gaseous form to the liquid form. And there are some experts in the room here on how to do that. And you think you've tackled a tough challenge. It was easy because the temperature at which natural gas liquefies, it is hard, is minus 160 degrees Celsius. The temperature that hydrogen liquefies is minus 253 Celsius. That's dramatically colder, so there are more stages of cooling that have to be gone through, therefore more energy is invested into cooling it. But once you've done that, you can ship it in a ship. The ships don't exist. So that top picture there is an artist sketch from Kawasaki, but I've been to Japan. Gustavo Gomberg was with me. We took a delegation, and we saw the factory where Kawasaki is building the tanks, which are the giant thermos flask tanks that go into the ship that they were building elsewhere. So that's underway, and that's going to be tested out soon. Alternatively, you can do a chemical conversion, and you can convert the hydrogen into ammonia. Now, ammonia is nitrogen plus hydrogen. The chemical formula is NH3. So every molecule of ammonia has just one nitrogen, but it's got 3 hydrogens. So it's a very, very dense carrier of hydrogen atoms. Once you've done that, you can use sort of off-the-shelf ships. That's a sketch at the top. That's a real ship from the Yarra Company. And they exist, and they just move ammonia around. It's quite easy at normal temperatures with just a couple of atmospheres of pressure. Ammonia is a liquid. It's toxic, but it's very commonly handled. The third way is you can do yet another chemical transformation into what's called methylcyclohexane. You think I wrote that just to show off that I can say methylcyclohexane, but it is seriously being considered, and there's a project that Japan is running in Brunei that is converting chemically hydrogen to methylcyclohexane. You start with toluene. Toluene, a standard petrochemical product. You add, that's C7H8, you add 6 molecules of hydrogen, it becomes methylcyclohexane, you ship it, you strip off the hydrogen, you're left with the toluene, and you send it back. So the toluene is a carrier that just shuttles back and forth. So it's quite a clever approach to doing it. And no one knows at this stage which of these shipping modalities will be the most cost-effective and efficient going forward at scale. They all work, but they haven't been done at the sort of scale that we're talking about. Why Australia? Why doesn't Japan make its own hydrogen? Well, let's talk about why Australia. We have an abundance. We have a lot of solar energy, wind energy, hydroelectricity. We're not building any more hydro, but of course you could use hydroelectricity to make clean hydrogen. But we certainly have huge capacity for solar and wind. In fact, the World Energy Council identified Australia as the giant when it comes to renewable resources, the giant in the world. Let's look at a map of Australia and its solar capabilities. I'm just looking at solar at the moment, and we'll have a little bit of a think about Japan. Australia, you know us, we're big. The scale from blue to red here is starting at 10 megajoules per square metre, going up to 24. So there's a 2.5-fold increase in sun per annum per square metre in Australia. And anywhere where it's yellow and red is a really good solar resource. Now, if I was to, by magic, take Japan from the north and bring it down to the south, and bring it from as far north of the equator to an appropriate position south of the equator, that's where Japan would sit. It's sort of like New Zealand in a way. So this is to scale. It's, in terms of area, it's the right scale and distance from the equator. They just don't have the solar exposure that we have. Plus, they have a lot of people. So we only have 3 people per square kilometre on our vast continent. They have 336 people per square kilometre. So even if they had the solar radiation, which they don't have the spare land to do it. And if you go to Japan, you see all the land is used for civilization, like roads and houses and bridges, or for rice paddies, or for their national forests. And they're very, very committed to their national forests. So they just don't have the resources that would enable them to make the hydrogen. And then they don't have the fossil fuels. So they can't make the hydrogen from any pathway. Question that often comes up, okay, if we're making hydrogen from water and we're making it in big scale, let's say we wanted to export as much hydrogen 20 years from now as we currently export LNG, is there enough water in Australia? Because we are talking, as I said, not glasses, but swimming pools every second. And the answer is yes. So let me just do an example of a small level of export of 2 million tonnes of LH2. LH2, that's liquid hydrogen. Now, per kilogram or per tonne, it's got about 2.5 times the energy density. So 2 million tonnes of liquefied hydrogen is energy equivalent of 5 million tonnes of LNG. So if you're using it as a fuel to generate electricity in Japan or drive a truck, you get a 2.5 to 1 advantage on a mass basis. So for this example, comparing it to 5 million tonnes, that's about a 10%. That's a tenth of our 2017 exports. Our exports are considerably more than that this year and going forward, but around about a 10% business. Just a modest, a big but modest ambition. That would require 18 gigalitres of water. And people say, well, that sounds like a lot. Giga is a big prefix. It's actually not that great. If you were to get the water by desalination, and you can, just the one desalination plant in Victoria that doesn't get used can produce nearly 10 times the amount of water that we need. So the Victorian desalination plant produces 140 gigalitres per year if we switched it on, which would be more than sufficient for the export requirements for 10% of the LNG industry. Or compare it to the Wivenhoe Dam, which actually holds 796 gigalitres. So it's a lot of water, but it's absolutely within our capacity to deal with. But it has to be managed properly. Now, we've been talking about the renewable pathway. We also have a lot of fossil fuels. We've got an abundance of coal, methane, and we have sites for sequestration. Remember, Japan, Korea, other countries won't buy our hydrogen if they're seeing us release all that carbon dioxide as a byproduct. So we have to do something with the carbon dioxide. In Victoria, there's a project that is currently committed in the Latrobe Valley. It's got $500 million of funding. It's underway. It's partly funded by the Victorian government, the Australian government, the Japanese government, and Japanese companies. And Gustavo's been an advisor to that project, where they take brown coal. Now, the beauty of brown coal is that once the last of the brown coal electricity generators close down, and they will, it is a stranded asset. There is no export market for brown coal, and the Japanese recognise that. There's virtually no cost in accessing it. It's alluvial. It sits at the surface. It's got a maximum of 10 metres of topsoil above it. They just take a scoop and go, scoop, conveyor belt, scoop, conveyor belt. So the fuel is virtually free, which is attractive if you're trying to make something, a product at high scale. So they can just scoop it up. Then the question is, what do you do with it? And this is a little bit washed out, but this is, I'll have to point to, this is the coast of Victoria, and this little area here is called the Pelican Field, where a project that's been going for about 10 years called CarbonNet has mapped out the potential to bury carbon dioxide in salt formations under a capping rock offshore. The advantage of offshore is that it's not in anybody's immediate backyard, because even if you can show people that sequestration is absolutely safe, they're going to feel uncomfortable. And so there's an advantage that the Victorians have identified in doing it in this Pelican Field, and then your carbon dioxide can come from the process of manufacturing and be buried in the seabed. So I've been talking about export, but of course there are domestic opportunities here too, which will be driven by how much we desire to decarbonise our system, but also by the ability of hydrogen production and use to contribute to stabilising our electricity system. So I'll talk about that too. If you look at our transition to renewable fuels, the jigsaw that makes it all happen is based on storage that we already anticipate, such as batteries and pumped hydro. Huge amount of scale-up still required. Rooftop solar, distributed energy resources, digitalisation, solar, wind and hydro for generation. But there are certain things that we can't do easily. First of all, we can't ship electricity, so we don't have the ability to ship sunshine with the existing capabilities. But more importantly, we don't have a solution for heavy transport, such as the trains that go from Adelaide to Darwin. We don't, or trucks, the B-doubles that drive from, say, Melbourne to Brisbane. We don't have a solution for high temperature industrial heating, and we don't have solutions that are adding to the grid resilience. All of these can be addressed by hydrogen. So in a sense, hydrogen is the final piece, the missing piece in the jigsaw puzzle through the transition. So let me just take some examples. I'll look at the major sectors in the Australian energy economy. Electricity, I'm not sure why it's going dull. Electricity, direct combustion, transport, agriculture. I'm only going to look at the top three. Electricity is the biggest sector for the generation of emissions, followed by direct combustion, that's heating our houses, water, industrial heating, and transport. Electricity, in Australia, we're not going to generate electricity primarily from hydrogen. In Japan, they will. They will import hydrogen and generate electricity. But there's no point in Australia taking electricity from a solar farm, making hydrogen, and then generating electricity, because you get a lot of losses, and that's the biggest scourge of the hydrogen production process. You get a lot of energy losses along the way. So we wouldn't do that here. But we will have, and already do have, excess electricity that we can use for making hydrogen for domestic purposes. And when you put these electrolyzers onto the electricity grid, they represent a fast load. The electrolyzers can switch on and off in a second or two, from operating at hundreds of megawatts down to zero, or from zero up to hundreds of megawatts. So when the wind is blowing, you can operate these. When the wind's not blowing, you just let them switch off. In a sense, an electrolyser for solar and wind is a little bit like an aluminium smelter for coal. We brought in aluminium smelters to have a constant load for the constant generation. Electrolysers are a variable load for variable generation, so it's a match made in heaven. The next one to look at is the transport sector. It's happening. This is a SUV from Hyundai called the Hyundai Nexo. It's really quite a lovely car. I had an opportunity to drive in one in Perth. It's got 800 kilometres range from one tank of hydrogen, so that's pretty good. For long distance transport, there's an American company called Nikola that is producing these big semi-trailers that can take a 40-foot container nearly 2,000 kilometres on one refuelling of hydrogen, which is very impressive. And the French company Alstom is now making trains that are in routine use in Germany on a 600-kilometre track. So a hydrogen train is very much like a diesel train. When you hear a diesel train, many of you might think that there's a diesel engine going with pistons up and down, but it's not. A diesel train has got a diesel electric generator and then electric motors. So a hydrogen train will be a hydrogen electric, just like a diesel electric train. And you need refueling stations. On the trip to Japan, I had the opportunity of refueling a car. Japan is committed to putting out refueling stations. There's a chicken and egg problem. Unless government gets involved in the first 100 or 200 refueling stations, the car manufacturers can't sell their cars. But no one wants to build the refueling stations until there are cars on the road. So this is an area where government has to assist. The third of the domestic sectors that I wanted to talk about is direct combustion. So that's where currently natural gas is piped into our cities and used probably for this building, but certainly in Melbourne and Adelaide and the southeastern and the southwestern cities extensively during winter for heating, for cooking, for hot water, etc. It works really well with hydrogen if you use polyethylene pipes, which is where the industry has been going for the last 20 years in any event, just for natural gas. But you need appliances. So I got to see the first hydrogen appliance that I've ever seen about 2 weeks ago in Adelaide. So that guy there in the apron is me, and this barbecue is a hydrogen barbecue. But you can't tell unless you zoom into my apron, which actually has the word hydrogen on it. This barbecue is powered just by a tank of hydrogen, which was behind the curtain over there. The remarkable thing, for all the scientists in the room, you all know that when hydrogen burns, it's a colourless flame. And yet, when I looked under the barbecue, the flame had colour. And the manufacturers were there and they can't tell me why. It's something coming out of the pipes, something in the air. It needs to be investigated. But it's a good thing because you prefer to see the flame than not see the flame. Okay, how do we capture this opportunity? So, as I said, or as Peter said, I had the honour to present a report to the COAG energy ministers, including the Queensland Minister, in August. And it was not a report with recommendations, it was just a report that set the scene, explained where the vision is, where the opportunities are. And a key part of that was Japan's interest. And in order to go to the next stage of providing advice, I felt it was very important to go to Japan, and I did with a delegation. And we went to Japan with 3 goals in our minds. The first was to assess the commitment of the Japanese government and industry to their national hydrogen strategy. They have a declared national hydrogen strategy that they published in December of last year. The second was to assess their technological readiness. And the third was to promote partnership opportunities between, or just at least represent Australia well as a possible partner in future. What we saw was very encouraging. In Japan, they don't just see it as a commitment to the Paris Accord, they see it as an intergenerational commitment. Whoever we spoke to saw the need for Japan to decarbonise for their children and their grandchildren, etc. And it didn't matter where we went, whether we went to government departments, to see university academics, or to big industries like Kawasaki and Iwatani and Toshiba. Didn't matter where we went, they all could recite the Japanese strategy almost chapter and verse. The commitment was fantastic. But they're not silly. They're not going to buy Australian or other liquefied hydrogen at any cost. So they've got some clear price targets, but they're long term. The 2030 price target, they express it in dollars per kilogram, but if you convert that to what we're more familiar with in LNG, $3 a kilogram is $21 per gigajoule. And their 2050 target, which is a long time from now, is $2 a kilogram, which is $14 a gigajoule. There are people in this room that would know the prices better than me, but I think they range from $8 to $16 over the years. So it's a high end, but within the range of what they're being prepared to pay. And I think it'll be achievable. In terms of technological readiness, they're doing a lot of demonstration projects. I don't have time to go through them all, but they're not yet at the commercialisation stage. So all the opportunities are open for us to partner with Japan, where we are an exporter and they are an importer. But the other thing that was worth commenting on was their commitment to safety. We had the opportunity to visit a company called Iwatani, which is their big industrial gas supplier. They handle hydrogen routinely for the last 75 years, almost without incident. But their commitment to safety was so clear in the way they constructed everything, and the pipes and the procedures. It's definitely a gas that can be handled as safely as any other gas. And in terms of the partnership, I think we were effective, but I won't go into that. All those roads lead to Rome, you know, but the price of getting there can be different. So the Japanese are exploring different ways of achieving their national hydrogen strategy. 3 areas that they're looking at actively: production, and as I said, that can be done from natural gas, which is methane, or from coal, or from electrolysis of water using renewables. All 3 of them are being investigated around the world, not just with Australia. Shipping, they're actively looking at all 3 of the shipping processes that I mentioned to you: the chemical transformation to ammonia, chemical transformation into methyl cyclohexane, or physical transformation to the liquid form. And in terms of generation, at their end, they're working with the big manufacturers to make gas turbines that can run on hydrogen rather than natural gas. It's not as simple as just changing the injectors, because the flame rates, the circulation rates, the temperatures are all different. But they're also looking at making turbines that can burn ammonia directly, which is a huge advantage, because then you can take the ammonia off a ship and not do a chemical reconversion to hydrogen and just burn it. And that could, for electricity generation at large centralised facilities, that could be the most economic way forward. But they don't actually know yet until they do it at really large scale. Finally, not quite finally, but I'm going to put up a few activities around Australia. Please don't try to read anything, it'll be too small. I just want you to get a sense that there's a lot happening around the country. Pretty much 5 of the states already have little pilot projects going. There's nothing large happening yet, but there are things happening, including the Northern Oil Biofuels Pilot Program and the Samuel Griffith Centre in Queensland. Queensland, I think you've got a long way to go, but you've started, and that's the important thing. We've all got a long way to go. The country's got a long way to go. And the longer something's going to take, I think the earlier you've got to put a step forward and get going. I mentioned the report that we gave to the COAG energy ministers, the national energy ministers. It drew upon a report that was done by ARENA on the export market. It drew upon a report that was done by the CSIRO on a technology roadmap. Both of those were inputs into the report that I led, and Peter was on the panel, for hydrogen in Australia's future. And that's what went to the ministers. And it went to the ministers on the 10th of August. And the minister's response on the day, which was really heartening, and Minister, I thank you and your colleagues, it was really heartening, was that the chief scientists working with senior officials will bring back a proposal for the development of a national hydrogen strategy to the next scheduled meeting, which is about 2 weeks from now, on December the 19th. They're not asking for the strategy itself. The strategy is going to take a year to develop. But they're asking for a formal proposal in terms of reference, consultation procedures, who the stakeholders are, and who will do the work. And that will be presented on December the 19th. My wife, Elizabeth Finkel, who's here, hates it when I do this, but I sometimes put aside my chief scientist hat and become a spiritualist. I have to point out the date, 10th of August, which is in numbers written as 1008. Does anybody know the atomic weight of hydrogen? It's 1. The atomic weight of hydrogen to 3 decimal places is 1.008. Look at that. That can't be a coincidence, can it? Okay. So if the ministers accept the proposal on December the 19th, this is the timeline that they will be accepting, that we're putting into the proposal. In January, the COAG task force, that's the working group, will be established and will get running. By April, we'll be out there with an issues paper and focusing on export. By June, we'll have an issues paper and we'll be doing a lot of consultation because we need to speak to virtually everybody in order to get this right. We'll have an issues paper and have done the consultation on domestic policies and measures. By August, we'll present that to the COAG meeting so they can consider the draft proposal. And then with the minister's permission, we'll start another round of public consultation on the full draft strategy. And then hopefully at the December meeting, 12 months later, the ministers will consider the strategy and be in a position to adopt it. The timeline for the strategy, or the time horizon, is primarily the coming decade, but it will clearly have to be thinking about the period out to 2050, if for no other reason than to complement the approach that Japan has done in its import-oriented national hydrogen strategy. Finally, just the comment to share with you that this will not be an overnight sensation. Everything in the energy system takes time. We're not talking about a few years, we're talking about a few decades. Think about the natural gas industry that you're all so familiar with. The first trigger point that I've been able to identify was 1979, when the Western Australian government wrote an offtake agreement with, I think, Chevron and Woodside. But the first drop of liquefied LNG didn't ship till 10 years later in 1989. And now in that 30-year period, we're seeing constant increases in our export capability, and we've got a mega industry. So 40 years from 1979 to where we are now. I think we can do this a little bit faster, but it's not overnight, it's not just a few years, it's decades, as it should be. To do it, we've got to work together. We've got to have a shared vision, and we've got to have domestic partnerships, we've got to have global partnerships, and we can do it in an ad hoc fashion, but I truly believe that if we're strategic about this, we can do it more efficiently and position ourselves as the most capable hydrogen supplier in the world. Thank you.
Can everybody hear me? Perfect. Thank you, Alan. As always, very inspiring. I'm here more as a moderator, and so what I'm going to introduce you to is to Gustavo Gomberg. He's going to respond to that presentation. Well, I've got a couple of questions, and then of course I'll open it up to the floor. But many of you, I'm not sure if you know Gustavo Gomberg. He's a director at KPMG's Deal Advisory Practice in Australia. He's a seasoned senior executive and strategist with over 20 years of international experience spanning emerging and developed markets. Gustavo is responsible for the origination and execution of complex energy and infrastructure transactions and projects, and he has worked as commercial and financial advisor to Australian and international utilities, resource sector clients and governments in transactions and projects worth more than 20 billion. He has been involved in accessing early stage capital for renewable power projects, emerging technologies and electricity industry reform. And Gustavo has been at the forefront of hydrogen development in Australia. When we were talking about the panel, Alan said we definitely have to have Gustavo. He's passionate about hydrogen and often known as Mr. Hydrogen. He's the lead advisor to Kawasaki Heavy Industries in their HYSTRA and HESG project, HES project, and was on the steering committee of the CSIRO National Hydrogen Roadmap, and is currently advising international and domestic clients on hydrogen strategy. So, Gustavo, welcome, and I'd ask you to respond. Thank you.
Thank you. Thanks, Peter. Thanks, Alan, for the opportunity, and thanks to KPMG also for sponsoring this today. It's probably not a great position to be in to talk right after our chief scientist, but I'll do my best here, so bear with me. I thought I would just reflect on the why now, and I was doing an interview yesterday with the University of Melbourne. They're looking into hydrogen as well. And there's probably 5 points that I'd like to make in terms of why now, what's different from last 50 years. The first, as Alan pointed out, is really Japan and South Korea really underwriting the market. Japan, Matti, we caught up with the minister of the ministry that is really responsible for the development of hydrogen strategy in Japan, and Matti is spending $2 billion a year just on hydrogen. At the moment, they don't think this is enough, and they will probably pump it up. But just to give you a sense of the dollars flowing into that, so the markets are not ready for an offtake. No one is ready to sign the dotted line, but the governments are really focusing on the policy, and the money is flowing into that. So there is a sense that the market will be underwritten in some shape or form in the near future. The second point is the cost of producing hydrogen is really declining. Part of that is obviously the cost of renewables has come down. So when I started working in the energy space in Australia, I recall probably 10, 15 years ago, the cost of solar was about $400 to $500 a megawatt hour. At the moment, it'll probably get a tenth of that price. So, you know, if we keep going down that path, and if we use curtailed energy, there's a sense that we might get to a point where, I'm not sure if we get to $10 a megawatt hour, but possibly 20, and at that level, we might see hydrogen really stacking up. So in my sense, and I think that's something that I'm hoping that the National Hydrogen Strategy next year will address, is that hydrogen needs renewable, but renewables needs hydrogen. So I guess we come to a point where there's a lot of discussion, and very polarized discussion here in this country about renewables and fossil fuels. We need everything. Hydrogen is not the solution, it's probably part of the solution. And I would expect that the strategy deals with that a bit. The cost of the application, I think Alan touched on this briefly, the cost of hydrogen application is also coming down. Just to give you a sense, we had a privilege to go to the Toyota factory that they produced the Mirai, the fuel cell vehicle, in Japan a couple of months ago. And very interestingly, we were, you know, the whole thing is very manual. The factory produced about 3,000 cars a year, so not a significant amount. And they were walking us through the factory. We unfortunately couldn't take any pictures, but we were sitting at a particular station. There was one person, just one person sitting there the whole time. And this person was responsible for manufacturing the door of the Mirai, so a pretty kind of simple task. It takes 58 minutes to produce the door of the Mirai. And that same door for a very similar car, the Corolla, in an automated line takes 150 seconds. So if we just take that into account and think about the opportunities to get the costs out and reduce the cost of the applications as well, it's quite significant. The third point is I think it's probably not new, but it's the ability for hydrogen for sector coupling, you know, to be able to be used for industrial feedstock, for transportation, for energy, And that's quite a flexible energy carrier, or a fuel, as Alan said. The difference now is that there are more technologies than we've had before. There are technologies to transport the hydrogen. There are technologies that have developed in terms of the application. So it's not just the cost, but the technologies are there. The fourth point I make is, and as a numbers person, the level of investment by the industry. So my sense is industry has started to put the money where their mouth is. A good example is, I think it was last week or the week before, Air Liquide has decided to invest $150 million to deploy hydrogen refueling infrastructure in California. Again, there is some subsidy behind this, but $150 million for an organization like Air Liquide, those things have to go through board. There's a lot of due diligence that is required. So that tells me that it's not just the Hydrogen Council with 53 companies behind it, but it's real money that is starting to flow into this. And the other thermometer for me is really people starting to spend money with advisors on this. So people start really to spend money with people like myself on real projects. So really glad to see that, and that tells me the sort of commitment that's starting to happen in real life. And the last bit for me, why now? I think there's a sense of excitement that we haven't had before. Whether it's governments, and obviously through a lot of projects that we've been dealing with, I've seen a lot of interest from both the federal government and state governments. I would probably say that there is largely bipartisan support for hydrogen initiatives. Obviously, governments are really interested in the economic development, the industry development behind this, the jobs. So I suppose there's excitement, and for me, the delegation to Japan was a one-off, was a significant milestone. Even the fact that we had, 15 people around was just an amazing week. We had a great time together.